Light, if you can hear me, we will get started. Okay. Seeing some people that are not there but are pretending like they are. That's interesting. Okay, let us begin with a little bit of a discussion of two input NAND gates, since that's going to be our building structure. Let me see if I've got a thing sitting here somewhere. There it is. So one of the things that we want to do is be able to intuitively see inside of the NAND gate the use throughout all of the logic gates that we're going to need to be able to create. We'll start with the combinational stuff. And of course, in a couple of weeks, when we get around to sequential stuff, we'll see that the NAND gate continues to work, does a good job there. So what we'll do is we'll go through and take each of the functions in turn. And I think we started doing some of this in the last class. We'll look at what we would need to do in order to build that structure and see if we can build all of the types of things that we would need. Let's start simple. And let's assume that what we want to build first is a NAND gate out of a two-input NAND gate. Okay, I mean, that's kind of silly to say, but basically that's it, we're done. So we can create a NAND gate out of a NAND gate in kind of an identity fashion. Now, of course, we have, I don't think I have any drawings of those, but we have a secondary way we could write the same thing, which is this. As long as we put bubbles here, we use the De Morgan form of the same NAND gate. These are equivalent to each other, and they both implement the NAND function, which if we build our truth table for it, is going to basically be take an and invert the function. So for an and, it would be 0, 0, 0, 1. So we're going to put for an and 1, 1, 1, 0. Now, when we're talking about these, sometimes we'll talk about what a gate is sensitive to. And in this case, the gate is sensitive to both of the values being a 1. That's when we get something different out of it. It's not always true that we only have one item different, but sometimes it's a good idea to keep track of what is the thing that a particular gate is sensitive to. Now, the next thing that we would want to be able to do, and we know how to do this already, is we want to build a NOT gator, or which is an inverter. We want to build that. Truth table for this is simple. It only has an A input. Because there's only one input, we'll have 2 to the first number of lines, which is 2. So A can be a 0, A can be a 1. Y is always the opposite of that. So when we have a NAND gate, in order to cause that to happen, we have to reduce the number of inputs down to 1. To do that, we look at our truth table, knowing that this case here is the one that's different. In order to generate a 0, we have to somehow get 2 1s to pass in as a single one. And of course, then any of the others, the 0, 0, the 0, 1, or the 1, 0, would serve to give us the 1. But it's handy that the 0, 0 also does, because that says that we can simply take and tie the inputs together, call that A, and Y will come out the other end. So we, in fact, can build a NOT gate or an inverter out of 2-input NAND gates. Naturally, the next thing we'd want to be able to do would be to build a buffer out of a 2-input NAND gate. Now, buffer is the opposite function of this. Basically, what goes in comes out. Now, you might think this is kind of a useless gate. It's basically the same picture as that without the bubble on it. One other thing we should make note of is while we're here, it's also legitimate to write an inverter with the bubble on the input instead of the output. This is more common, but there are times when you might do that, and it is correct. So the buffer, for our purposes here, let's think about what you actually use a buffer for. Have we discussed that in class? Does anybody remember what the use of a buffer gate is? Samir?
Is it to make sure not like too much power goes through?
Well, maybe. I'm not quite sure what you're saying. Can somebody else explain what he's trying to say there a little more clearly? Sargon?
Is it for the signal amplification?
Right. That's probably the most use of a buffer that we're going to see. That and the protection of a device. Sometimes we'll put a buffer in front of a very expensive piece of equipment so that it's the buffer that blows up and not the expensive piece of equipment. But more likely, let's assume that I have some sort of a black box circuit over here that produces a signal that more than one person is interested in. Let's say that this particular signal is limited to only 10 people listening to it. That means we can hook it up to 10 inputs. I won't draw all 10, but 10 inputs. What if we need to do 11 inputs? Well, a buffer is intentionally designed so the number of inputs that can be driven by its output is bigger than the standard device in that technology. So if normally there's 10, a buffer might support 20. And that says that we could take into this one of these signals and then fan it out to 20 more signals. So if we had 10 here, 20 here, we could actually feed 200 devices by taking each of these and having their output buffered. Now, we probably wouldn't do that, but it's possible. So a buffer needs to be built from a NAND gate. So let's draw a NAND gate over here again. And let's think about a way we could do that. And the first thing that comes to mind is we have in our Boolean equation list something that says y is equal to the buffer function, which is a. But do you remember in the Boolean thing, we also saw something that said a is equivalent to a inverted twice? Give me a green circle if you remember that particular identity. Okay. So if it says invert twice, let's do that. Let's build a circuit. You can take an inverter and run it into another inverter. Now, can we build an inverter out of an AND gate? Well, yes, we can. So if I took, oops, wrong guy, it's this guy. I put two inverters in a row, or I should say two NAND gates, turn them into inverters, where this is A and this is Y, we will have created basically a buffer circuit or buffer gate. Did everybody see what we did there? A becomes not A becomes A. So it's the same as putting two slashes over an A to get the A back again. Now you might say, why not just hook Y to A? Well, you would if you didn't need the buffer function. And in this case, we've implied that we need a buffer. And so let's see how we build one. We can't build one with two input NAND gates with no two input NAND gates. Okay, let's continue on here a bit. I think we did this one last class, but just as a review, what if we want to build an AND gate out of a NAND gate? Okay, let's think about that a second. An AND gate looks like A multiplied times B, or A ANDed with B. And that's the AND gate. A NAND gate, one of the ways we can draw it, is as an AND gate that's an AND with an inversion on it. So if I have this, which is a two input NAND gate, and I want to make it look like that, I need to take the function and doubly invert it, which will basically get rid of the inverter, leaving me with the AND. So there's the NAND. Oops. There's an inverter. So this inverter gets rid of the dot, which means that A and B here, when we look at them here, will be Y. So we build an AND gate out of NAND gates. Does anybody have any questions this far? Okay, you have a question, Frank?
Yeah, I guess I have one question. Why wouldn't you just simply use an AND gate as opposed to basically using a double negative?
Because remember what an AND gate costs relative to a NAND gate. If we're going to be doing, what the project calls for, and they say build everything out of two input NAND gates, we use NAND gates. Okay. Yes, you can get AND gates. You can buy them. They're just more expensive. And also internally, sometimes when we get to field programmable gate arrays later in the semester, you'll see we don't really get a choice. We're going to get a field of ands and a field of nots from which we can assemble NAND gates, from which we can assemble any circuit we need to. So sometimes we don't even get a choice. Okay, let's move ahead. Could you give me a green circle, please? Peter, give me a green circle. Okay. Let us. Next reasonable thing we could do would be to build an OR circuit. Now we know an OR looks like that. So put your hand up if you know of any way that we can turn our NAND gate into something that looks like an OR. Okay, I see three people that have an idea. Okay, we go way to the top of this and we say, what were the pictures we had of NAND gates? We had two types. We have one that looks like this. Notice it's built on the body of an AND gate. And we have one that looks like this. Notice it's built on the body of an OR gate. So this would be an OR if we could get rid of those bubbles. So that's a NAND gate. Now to get rid of the bubble, we have to add one more inverter. So we hook to this leg. We need to add an inverter made out of an AND gate. That's tied together. And to this leg, we need to add a NAND gate, which has been made out of as an inverter. And then we'd have an OR gate. Let's redraw that with a little better looking diagram. So these guys here connect to this, because if this is a NAND gate, this really has bubbles here that we want to get rid of. Remember, two bubbles in a row, get rid of the bubbles. There's two in a row, two in a row. Since we only have two inputs, this has to be A. This has to be B. Of course, this is Y. And that means we've built an OR gate. So how about a NOR gate? Well, we have an OR. We need to invert it. So let's draw that again. That's A. That's B. Now, there's bubbles here because this is a De Morgan NAND gate. The signal here needs to be inverted one more time, right? A NOR is just the inversion of an OR. So we should be able to add out here another NAND gate, and that will be Y. This is a NOR gate built out of NAND gates. Now, since more complicated circuits, as we've been saying, things are always sums of products in our world. So y is always equal to something ANDed together, ORed with something ANDed together, ORed with something ANDed together. As long as we can do ORs and ANDs and invert, we can build these. And since all our equations can be stated in terms of these, any simple combination piece of logic can be built with 2 input NOR gates or NAND gates. It could be built with NOR gates also, but for our purposes with 2 input NAND gates. So we want to keep that filed in our head because that's a useful thing to know. That's also why we really want to get the minimum of these, because the minimum sum of products, because then we have less pieces we have to build. Now we could sit here and write a XOR and build that, because a XOR is just simply one of these guys. And as long as we can express it as a sum of products, we can build it. Now you should be able to do these even if you don't have them in front of you. You should be able to sit down and think your way through one of these types of gates that we have here. I would expect you to be able to do that. Robert? Okay. What's going on here? Oh, I'm pushing the wrong key. I have to restart that. Now, we might have done this before, but I'm going to do it again anyway. Let's do it on a notepad to start. I think we've probably done this in here. The majority function, does that remind anybody of anything we've talked about before? Give me a green light if you remember the majority function. No? Okay. Well, all the majority function is it says I'm going to be a 1 or true if the number of inputs that I have has more 1s than 0s. And that's the majority function. Now, when we're going to write a minimum sum of products for this, what we know so far to do is to take out of here the fundamental products, which are also sometimes called min terms, and write them as simple product terms. So the first one we get is y. Whoops, I thought I typed down there. Y is equal to not A, B, C. 0, 1, 1. Not A, B, C. That's a 1. And what we're saying with these terms is this, when true, gives me the value true, or this, or this, or this, where each one is simply a combination of all the elements that go to make it up. So our second product term will be the next one that we find. Or A, not B, C. Or A, B, not C. Or A, B, C. And we should be able to pull out an expression, which is true. This statement is true. Either this, 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 or this is going to make this true. Now, in the case of this, it's been written in a way that 2 of these can never be true at the same time, but pieces of them can. Now, one of the things we did with this is we algebraically sat down and extracted, using Boolean algebra, looking to find what terms could be gotten rid of. In last class, we discussed using the Karnow mapping system for being able to reduce an equation like that. And I want to talk about it for a couple of minutes here. Let me get a Karnow map here somewhere. We have A, B, and C, where we have labeled the top row is not A, the bottom row is A. Then using a gray code-like sequence, we label invert, 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 don't invert either, don't invert, invert. Now let's become familiar with this in a way. Put your hand up if you can. I'm going to actually, let me number these squares for a second here. This is 1, this is 2, this is 3, this is 4. And I'm not using the sequence we put things into the squares. I'm just simply numbering them. Now raise your hand if you know where A lives inside of those boxes. Which boxes are represented by the single term A? Raise your hand if you know. Okay, Scott, what do you think?
5, 6, 7, and 8.
Right, so A takes this bottom row and owns it. And the reason it owns it is because there's no not A's in it. And in that whole row, B is an invert and a not invert, which wipes each other out. C is inverted and not inverted, which also wipes them out. Now, what if somebody asked you where B was? Raise your hand if you know where B lives. Stephen?
The inverse or like just
Where is B?
so I'm guessing isn't it 1 through 8? It's just all of them because B is in all of them.
Nope.
No? Okay.
Frank, what do you think?
It's 3, 4, 7, and 8.
Exactly. Okay, B lives in this chunk right here. Where does not C live? Mikhail?
1, 4, 5, and 8.
Yeah, 1, 4, 5, and 8, exactly. Okay, now how about if somebody asks you where not A, not B lives? Patricia?
1, 2.
That's it, exactly. So we're able to just by name look at this and figure out where things are. So we should be able to, looking at our equation we just wrote, figure out which squares are accompanied by these particular values. Now, since we have 3 terms, we're only going to take up 1 square over here. If we had 2 terms, we'd take up 2 squares. If we had 1 term, as we saw, we'd take up 4 squares. And that numbers will be similar to that for no matter how many inputs we have. The fewer inputs we have, the more squares they take. So look at this equation for a second and then figure out which boxes are going to be highlighted over here. There's 4 boxes going to be turned on. So see if you can come up with the numbers of those boxes. Raise your hand when you have the numbers. Mohammed?
Professor,
Where's the first guy? Where's this guy?
it's number 4.
Not A, B, not C. That doesn't match.
Oh my bad. It's actually not A, B, C. It is the number 3, I think.
Okay, that's correct. Okay, so he's going to be a item in number 3. Basu, what is the next one going to be? We're not hearing you. Robert?
Oh, I'm sorry. It's number 6. I forgot to turn on the mic.
Okay. The next guy, A, B, not C. Emulin?
It's 8.
A, B, not C is 8. And then finally, A, B, C. Samir?
7.
Okay, so we should be able to go to 3, 6, 8, and 7. Let me erase these things that are here. There's 3 is going to get a 1. 6, 8, 7. Almost erase the numbers before we put our thing in. Now, what we want to do next is group these to see whether or not we can reduce the number of product terms we have down here, and in the product terms, reduce the number of individual items in the product term, the number of inputs per product term. So think about how you would combine these. Remember, you're going to draw circles around 8 if they will go together, 4 if they're in a box or a row or a column, 2 if they're in a column or a partial row in this case, and anything left would be a 1. As you go, you always make sure each new box you draw picks up new material. And when you're done, you make sure that no boxes are completely consumed by other boxes, meaning they, if you take the other boxes, completely cover everything they are trying to cover. So who's going to tell me what my boxes should be here? Here now?
The not
What should I
A, B,
combine?
C. Huh?
What should I be combining here?
The not A, B, C, and the A, B, C.
So
the
that's
A,
these two?
yeah.
Okay, so they're going to be combined into a box.
The A, not B, C, and the A, B, C.
Okay, we can let them overlap because it gains new material.
And the A, B, C, and the A, B, not C.
And we can let them do because they're gaining new material. Now, when we go back, we make sure that every box has something unique to it, and they do. So now we should be able to write out an equation which is smaller than the original one. Think about that for a second, and when you know what it is, raise your hand. We'll give everybody a couple seconds here to figure this out. Okay, Patricia, what's the name of this little box right here?
A C.
Right, B changed between the two, so C stays around, A stays around. So it's AC. Or we have this vertical one right here. Let me have Matthew tell me what that one is.
That will be BC.
Right, because it has both A's in it, so they cancel each other out. And then finally, we have one more going here. Stephen, what is that?
AB.
AB. Okay, so this is a minimum sum of products because we followed our rule. I know it looks like, well, we could rearrange it to say y is equal to A, C, or AB, or BC. And then we could say y is equal to A, C, or B, or BC. But why wouldn't we do that? What's our reason? Dante, why not?
Because doesn't it actually, can't you do that? Because doesn't that, can't you simplify? Oh, because you can't actually simplify it any more than that. It's the same. It basically says the same thing as our initial equation: the AC plus BC plus AB.
Right, but more importantly, this is not a sum of products. This is a product of sums taken as a sum of products. So this is not useful to us. We have to stop at the sum of product where we have terms that are ANDed, ORed with things, and that's it. So let's now take as a challenge here building this guy using 2 input NAND gates. This guy, so we're going to build y is equal to AC or AB or BC. We can draw the bus first, or we can draw the equation first. We have two things ANDed together. I'm sorry, two things inside each ANDed together, where their result is ORed together. And then we have a third thing, which is going to be ORed with the original guy's answer. And we can do that because associative law holds true, and we're doing ORs. So let's first of all just simply write out what we have here. We have three things ANDed together. Here's one of them. Here's two of them. Here's the three of them. First two are then ORed together. Then the result of it, which is the output of that OR, will be ORed with the last guy. So if we don't do no optimization at all, meaning we leave everything as ANDs and OR gates, this is Y. And these guys are hooked to A, B, and C. So let's draw our bus over here. We have an A. We have a B. We have a C. And by observation, I'm going to tell that we don't have anything inverted yet, but I left room that we could put them in if we need them. So this line is A. This line is B. This line is C. So this guy hooks to A and C. A, C. Second guy hooks to A and B. A, B. Last guy hooks to B and C. B and C. Now this works. This is this function. But now the teacher told us we have to use 2 input NAND gates. Well, we took care of the 2 inputs already, so we need to turn these into NAND gates. to make this look like a NAND gate, who can tell me what I have to do to it? Andrew?
You put a bubble on the front.
Yeah, put a bubble on his nose here. But I can't put a bubble by itself because if I do, it'll change what this is doing. So I have to put two inverters. I can put one here, and I can stick another inverter in here. Or because I know that these things, when they have bubbles on their inputs, are NAND gates, I could just simply put the second bubble right there. Do the same thing here. Now I've converted all three of those to NAND gates. I can come down here, invert him, and invert him. And I'm getting close to being done. The problem is I can't put a bubble on this guy's nose because he looks like an OR gate. I can put one here, but if I put one here, I need a second one to cancel it out. So I'm going to have to put one here. And then right in here, I need to put another inverter. I'm going to draw it like an inverter, even though we know we could make it out of a NAND gate. Oops, I got kind of a big one going there, but there it is. And we know we can build that out of a NAND gate. So we have 1, 2, 3, 4, 5, 6 NAND gates in order to build this circuit. Now, the types of chips we would be using have 4 gates per chip. So to build this function, I need 2 chips and I'll have 2 extra gates when I'm done that I could use for some other piece of my circuit. So as we went here, remember in the case where we were building all the functions, we needed to add things that did inversions because we wanted to change what the function did. Here we don't want to change what the function does because we write it out looking like exactly what it is. We have to then take care of making sure anytime we invert something, we doubly invert it to get rid of the inversions. And if we can make things look like this guy or that guy, we know that we're done with those. Those are already NAND gates. This guy is a NAND gate, but we can only put the bubble on him because we added an extra inverter, which of course we know, we can build that out of, I can replace this guy here with one of these where I tie the inputs together. And now he becomes an inverter. Any questions about that? Robert?
Yeah, when you draw the NAND gate as the inverted OR gate, or the OR gate with the 2 inverted inputs.
Right, the De Morgan equivalent.
Yeah, so, but from a actual hardware equivalent, there's no
exactly
it's the same exact thing.
They're identical.
We're just drawing it this way here to show the relationship to what we wanted to do with the OR.
Right, we needed this gate to do an OR, not an AND. So to make it do an OR, we have to make it look like an OR.
Okay.
For instance, if we had written it as an AND in here, the circuit wouldn't have worked because we would have had inverters in the wrong place in order to get it to fit there.
Okay, but at the end of the day, when we're building this, we're still just going to be putting, these are all just going to be the same thing.
This guy here and that guy might be inside the same chip, just 2 of the gates.
But they would come out of the same box and be the same piece, really.
It'd be the same chip. Yep. Okay, we haven't gotten enough information yet to, let's see, SN70, LS74. doing something on my other screen if you're wondering what I'm doing over here. If I were to go buy one of these, this is the data sheet for one that has the thing in it. It's showing me what one of the gates looks like, and then what the pinouts are for the particular gate that we're using. Now, it may or may not have packaging information in this particular data sheet. Now, just simply saying that all of the gates that are inside here look exactly like the one we've been using. And sometimes they show the innards of the chip. Let me see. No, they don't have where I'm looking right now doesn't have it. In a couple sessions, we're going to be talking about those chips in particular, and you'll see that, yes, indeed, they are exactly the same. Okay. So this was not that hard to build. We could, for example, on an exam or something, be given a question. Like y is equal to not BC or AC, or B not C. We might be asked, is that a minimum sum of products equation? Why don't you see if you can figure out a way to determine that? And then we'll move ahead to the next thing. So the question could be, is that a minimum sum of products? When you think you know the answer, raise your hand and make sure you have an explanation of why. With what we know, probably a good place to start would be with the Karnow map. So let me label this while you're thinking about that for a second. How did I know it was a 3-input equation? That's kind of a philosophical question for you to answer. So how did I know, Patricia?
When you use the kernel map and then you put in the inputs inside the boxes, you would find out that it's already the minimum sum of products.
Okay. How did I know that it was a 3-input equation? Jay?
Is it because like there are 3 letters in the equation?
Because there's 3 letters in the equation, what I know is it has to have at least 3 inputs. We don't know that there's not a D, an E, an F, and all those that just got eliminated in some of the algebra of defining the equation. So we don't really know. But in minimizing the equation, if those turned out not to be worth anything, then we would have to account for them, and this could be 8 or bigger. For example, an example of that with my cat. This is one of my good ones here. Okay, here I am. I'll be A. We'll make my cat be a B. And over here is Y. Y is whether the cat gets her way or not. We know there's obviously going to be 4 possible things that we could do. We also know that if the cat doesn't want to get her way, she's not going to get it. She does, she does. She doesn't, she doesn't. If she does, she does. You notice that I have absolutely no bearing in what happens. Doesn't matter what I want to do. Whatever the cat wants, the cat gets. So in this equation here, why build the A circuit at all? You don't have to. All you got to do is build B. But when it's presented to you, this may be the equation that you reduce and learn that from. We don't ever know what this was reduced from, but we do know that we can take and stick them back, as she was pointing out a second ago, back into the Karnow map and see if we have a minimum. Okay, not B, C. Well, not BC looks like it lives in this column right here. AC. Well, AC, and of course they're circled because they're a unit. AC looks like it would be in these two. Then B not C looks like it would be here. Now, is every box as big as it can be? Is there any way we could combine 4 of something together? And the answer is no, you can't. So does every box add some new material? Absolutely. So we have somehow stumbled upon the minimum sum of products for this particular equation right here. What if you were also asked then to put this into the truth table? Let's grab the truth table over here. Where in the truth table is not BC? Who can describe where I'm going to be looking? What's the general rule? Dante?
You'd be looking for not BC, where B is 0 and C is 1.
Right. So B is 0, C is a 1. There's one of them there. So we know that's a 1. The 0 and a 1 here. So there's the other one. And we know it's in a box of 2 because that's what the Karnow map did. Now we need AC. A has to be a 1. C has to be a 1. All the A's that are 1s are here. C's are 1 here, which already has a 1. And here. Whoops, not a 2. And then finally, B not C. What am I looking for here, somebody? Minotti?
Do you want the line where you would put the one, or do you want me to describe what?
I'll describe what this means.
So basically, B is 1 and C is 0.
Okay. Where is that?
Line number, row number 3. Yeah,
Got
this
one
one.
here.
And the second last one.
Okay. And we know the other lines in here are either zeros or don't cares.
Yeah.
Okay. So you can kind of move all the ways through those, and you're doing pretty good with doing that. The only problem we really have with Karnow mapping in general is as it gets bigger, it becomes harder because sometimes you're going to work with more than the 16 squares we have. So for example, again, if we take we say this particular plane right here is not A, and this particular plane right here is A, and we have some ones in our Karnow map, what we have to do is draw three-dimensional circles. We know that this plane right here is going to be circled and grab 4 items. We know that this right here is going to be circled and grab 4 items. Now, these two and those two are sitting directly on top of each other. So they could be combined in a group of 4. We won't, though, for what reason? Matthew?
You're not grabbing any new material.
That's right. Now, if I had done them second, it would have appeared I'm grabbing new material. It's not until I grab the third one and go back and look at them all to see that that one is completely taken over by the other one. So what would the equation for this particular square here be? Figure that out. And same thing with this one. What would the equation? I'll label this box over here because I don't have room to put it in here while you're thinking about it. Has 5 inputs for the function that's inside of here. So this guy, and you can just read these same labels off of this guy, sits on the not A plane. So y is equal to not A and whatever these are. Well, these are represented by C and E. Or this guy right here is on the A plane. And he is also has C in him, but he has D. And this would be a minimum sum of products for that 5-term item. Now it becomes more complicated, obviously, if you do have to dig down from layer to layer, or if you wrap around corner to corner, or if you have 6 inputs, in which case we have to have 4 maps, each of which are derived by A, B's, so that we have not A, B, not A, not B, not A, B, and A, not B, in a stack that looks a little bit like a Rubik's Cube. So we need a better technique for doing the multiple input or multiple layer type of things. And we have a technique for that. We're going to look at that tonight. Anybody have any questions about Karnow map before we move ahead? Because we're going to do all small problems, but they'll be extendable to large problems. And we'll be able to check our answers with Karnow maps. So you'll want to make sure you're pretty good at doing Karnow mapping. Okay, well, it looks like everybody's in pretty good gear here. Let us move ahead. Okay, let me see if I can grab this without losing you all. Okay. Years ago, and I'm talking years ago, one of my students, Gautam Singh, became very intrigued in the Quinn-McCluskey algorithm. And so the next semester, I had him come back as a guest speaker and present the material. And to do that, he presented it as a series of PowerPoint slides. One of the things you'll notice is this is such a very old version of PowerPoint that a lot of things don't work anymore. You look around the edges, you're going to see there's text and things that gets compressed, things that get smeared, but the main body of the presentation is still here. And he worked really hard on it. So he's one of the students I bring back routinely because I would have him come to class with us if he hadn't gotten a really, really good job and moved away. So you may be one of these people someday that I call back. So, you know, just kind of in the back of your head say, congratulations, Gautam, you did good. Okay, so let's talk about Quinn-McCluskey. We'll use his slides here, and then I will give you a copy of these slides on Blackboard under lessons after class is over tonight, and you can use them as reference material. As a matter of fact, the last slide is actually a homework assignment, and you'll be able to do that. And whether I have you turn it in or not, we'll see. Just make sure you have it prepared. Okay, Quinn-McCluskey. First of all, this is the early 1950s. The guy whose last name is Quinn was a very, very eccentric mathematician. Nobody could ever pin him down and get him to pronounce his last name correctly. He would change the way he said it every time he spoke to people, just to aggravate people. But he was a brilliant man. He got an algorithm which works, and it was extended later, several years later, by the guy McCluskey. I don't remember their first names now. You can certainly look them up. They have a presence on the web. And the algorithm's intention here is to be a more programmable, because the current Karnow maps aren't really handy at being programmed in computer languages. They tend to lead to a lot of mistakes. Whereas Quinn-McCluskey is very rigorous and very ordered, and also can handle huge numbers of inputs, where we're kind of stopping at 6 because we don't want to jump into 4 dimensions. In the Quinn-McCluskey algorithm, we just continue doing what we're doing. It just takes longer. So let's take a look at some of the things we need to do and learn about it, and see if we can kind of pick up on what's going on here. Now, it's a little bit different way of doing things. So just because you haven't seen it before, don't let it, be something that confuses you right out of the box. Just kind of hang on, and it'll start to make sense after a while. Once again, it's going to take advantage of the fact that things differing by 1 bit are important in reducing things to a minimum sum of products. So step 1, we're going to take these 7 steps, which basically are to find what are called the prime implicants. And we'll learn what a prime implicant is eventually. So first of all, we're going to look at our truth table, and we're going to identify all the lines that are minterms, meaning end with a 1 or end with a don't care. They either have an X or a don't care in their truth table. All of those are called implicants. Now, from the implicant set, we're going to find what are called the prime implicants. And some of the prime implicants are going to be what we call essential prime implicants, meaning they're absolutely necessary. Because just like with the Carnot problem or any sum of product reduction, depending on which boxes we pick, we may decide to pick boxes which overlap in different ways, and there could be different solutions to the same problem. They will all have the same number of minterms, and they will all have the same number of inputs in each of the implicants, but they could be different names. And we'll see how that could be used to our advantage also as we work with these over several classes. So assume we have a truth table. We find all the rows in the table that are yielding y equals 1 or y is equal to x, meaning x being we don't care what it is. Now, we're going to sort those rows as we identify them by the number of ones in the inputs they have. So let's assume I had a 4 input item and it had 0, 1, 0, 1 is equal to 1. 0, 1, 0, 1 has 2 ones inside of its minterm. Plus, of course, it yields a 1 as its output, but we don't count that. So that is going to go with any other minterms that I've identified that have 2 input bits as 1. Now, that won't make a lot of sense yet, but just kind of file away in your head that somehow we're going to identify each of the terms that have a 1 as their answer, and we're going to sort them by the number of input terms that happen to be 1. This is going to help us identify the terms that are adjacent to each other, because if I put terms that have 1, 1 against those that have 2 1s, we know that it's only possible for one term to have changed. We're kind of imposing gray code on them in our implicant list. Now that we've separated our implicants into kind of little buckets where all the ones that have 0 1s, all the ones that have 1 1, all the ones that have 2 1s, we're going to be able to compare from each group to the next group, assuming they differ by 1 bit, all of the ones that have a 1 bit with all the ones that have n plus 1 bits. And again, that'll make more sense when we do an example of it. But it's key on us identifying what is similar and what's not. Because we're looking to see which of those combinations of bits only differ by a single bit. And if it does, I have to take a sip of coffee here. I'm losing my voice again. We have to replace the bits with an X. Now, this X, unfortunately, is also the same as a don't care X, but it doesn't mean the same thing. So we'll see that it only appears here, so it won't be confusing when we're using it, but it does have the same spelling as the other does. Now, anytime we have a match, we're going to do step 4, which is basically we're going to check off that that implicant has been used, meaning we've generated another implicant which is smaller in number of terms, and we won't have to reuse this one again, other than in finishing up our comparisons. But we won't have to generate or use it as an implicant again. It could be in doing this that we generate some duplicate implicants. If we do, we just cross off the duplicates. Now, just like a good shampoo, we lather, rinse, and repeat. We're going to repeat steps 2 through 5 until we can't combine any more min terms. Now, anything that can't be combined and is left unchecked at this point is at least a prime implicant. It might be an essential prime, but it's at least a prime. All the other implicants now will not be necessary in the final answer. Some of the primes will be, and those we describe as being essential will certainly be, but there'll still be possibly some primes that go into the final answer. So I assure you that if you were not glazed over now, you weren't paying a lot of attention, because that's a lot of steps without seeing a picture of it happening to be complicated. But we needed to list them all somewhere so we could come back to them. I'm not going to ask if there's any questions, because if there weren't, you guys would be probably having had done this before. Step 2, of course, now is let's do something with our primes, which is to find the essential ones. We're going to make a chart, which is called, and the name is not here, but it's called the table of choice. He calls it the prime implicant chart. The min terms that need covering will be the columns. The prime implicants that came out of that last step 1 will be the rows. We'll order the rows by least number of terms to most number of terms. We also will put in the columns only the items which were true, not the items that we don't care. So do you remember in Karnow mapping how we had to decide whether an X was best served being a 1 or best served being a 0? Well, in Quinn-McCluskey, the algorithm does it for us. So while we have to tell it in the truth table and in the original implicant list where the don't cares were, when we get ready to do the table of choice, we don't want to have to cover them because they would be unnecessary. So we don't list them as columns. Now, once we've got our table built, we're going to look at the columns and see if there's any prime implicants that exclusively cover that implicant or min term. Because if it does, those are our essential primes. They are absolutely essential in the final answer. We can't not use them. So we'll put a check mark next to them, and we'll also check off any of the columns that they cover. Now, the remaining columns we get to pick from, trying to reduce down to the minimum number of necessary prime implicants to cover them. So we ourselves will have to get rid of any overlapping or any implicants that add no new material, which we were doing already in the Karnow problem, but it could be, because we're doing it graphically here, a little more simple to do. Although we have multiple answers we could derive from this, and it's up to us to pick which one is going to give us the best answer, because the best answer is going to be the one which is the minimum sum of products. So let's look at an example, because again, if you don't have questions about that page, you weren't paying attention or not here. Now down at the, notice at the top, the text, this used to say something, but over the years that has gotten crushed by the various versions of PowerPoint through which this has passed. So we're going to take and we're going to build a way to check our answer. Now we're going to do a simple 3 input problem rather than trying to jump immediately into a 6 or a 7 input problem. But this truth table, 0, 1, 1, 1, 0, 1, 1, 1, is this table right here. Now we can see that that is going to be a group and that is going to be a group. Because it's small, we're able to see Karnow-wise which ones we're going to use. So what we're going to do is we're going to go to the truth table. We're going to find every row that ends in a 1 or an X. In this case, there are no X's. And then we're going to group them by the number of bits that were in the inputs. So 001 has one input turned on. It's true, so we need it. We put it over here under 1 bits. 010 has 1 bit turned on. We put it over here. 11 has 2 bits turned on, so it's going to go in a set called 2. 101 would be in the 1 bits, but it's not turned on. 000 would have been in a group called 0 bits, and it's not turned on, so we don't need to worry about them. This one has 2 inputs turned on. This has 2 inputs turned on, so they're going to appear in this as implicates. And finally, the last min term here will appear in group with 3 bits turned on. So we have 2 1 bits, 2 2 bits, 1 3 bit, no 0 bits. And of course, the other rows that we have did not wind up over here. Those were not min terms because they didn't have as an answer a 1. Now, does anybody have any question about how I got from this table to this table? Now is the time to ask. Okay, I want everybody to turn your green circle on for a second. Okay, thank you. We had some problems with people not attending and just recording sessions. Recording is only under very exceptional cases even tolerable, and it'll probably in the long run cause that person aggravation. Or, you know, so don't assume you can record and just go away and do something else. You need to be here anytime that I call for a green light call like that. We lost at least 2 people tonight because they didn't have their green lights on last time I asked. And they probably turned the recorder on, then just left. So, you know, that's no good because that's not the way to learn this material. Okay, let me get off my soapbox there again. So the next thing we have to do, and let me talk about what it is we're going to do before we do it. I'm going to take the first implicant. I'm going to look at every item in the second group. And if I am the same as them except for 1 bit, I'm going to create a new group, another column, which is the same where we're similar, but has an X where we're different. So do you see the first guy and the first guy here could be replaced with 0x1? Give me a green light if you see that. This guy matches that guy as 0x1. They're different by 1 bit. This guy and that guy match as x01. This guy and that guy are different by 3 bits, so they don't generate anything new. But because he generated some things, he's going to get a check mark, and the first 2 here will get a check mark because they've been replaced by something else in another column. This guy hasn't been replaced. However, now we have to come back to this guy. He is going to compare to this guy and match 01x. It'll go into the set. He matches this guy. No, he doesn't. There's 3 things different. So had this guy not been checked off already, he would not get checked off. This guy and that guy matches x10. Both of these would get check marks. At this point, everybody here and everybody there has check marks, but we still have 1 guy to deal with. This guy matches him as x11. This guy matches him as 1x1. And this guy matches him as 11x. So everybody now in this column has got a check mark, and we've generated a new column. The new column looks like this. Now we're not done because these guys and those guys may differ by 1 bit, in which case we can combine them. Now, I need to compare this guy against all 3 of these doing the same exercise. If he matches anybody, he gets a check, they get a check. Same thing with him, same thing with him, same thing with him. Each one gets matched against all 3. Now, it turns out that the little shortcut here. Notice the X in the middle? That means he can't match any of these that don't have an X in the middle. So we know he won't match this guy, and he won't match that guy. So 0x1 can only match 1x1, and they differ by 1. So they're going to generate a new guy over here called xx1. Check, check. This guy can only generate something based on the first guy. xx1. xx1, the same as the last value, right? But it's 2 different guys. So he gets checked, he gets checked. This guy can only be compared against the last guy. x1x. We can write that down, x1x. Check, check. The last guy can only be compared against the first guy again. x1x. So he gets an x1x. They both get checked. So it looks like everybody here compared against somebody, but now we're going to generate items which have 2 X marks in them. Now, do you notice these 2 guys have the same value? These 2 guys have the same value. So nobody can be compared, but because the X's are in different spots, but also we notice since these are the same, we can get rid of one of them because it's a duplicate. So we can delete the duplicates, leaving us with only these 2 guys that can't be reduced. They become prime implicants. Have you followed the flow from left to right here? We would have now finished step 1 of his pages earlier. Think about that a second. Make sure if you were left in a room with only a truth table, a bottle of isopropyl alcohol, and a pencil, you could solve this problem. Kind of like MacGyver. Okay, let's do step 2. We got to build the table of choice. These identify the rows. These guys are the columns. There's our 2 prime implicants. These are the guys that are in the table over here that are 1s. They would not include any don't cares. Now what we have to do is figure out whether this guy covers a particular guy or not. First guy, yes, he does. Second guy, no, he doesn't. Third guy, yes, he does. Fourth guy, yes, he does. Well, this guy, no, he doesn't. This guy, yes, he does. Basically, he's saying anybody ending in a 1, I cover. Him, 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 and him. This guy says anybody with a 1 in the middle, I cover. Him, 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 and him. Now, there's an overlap, but what we're looking for here also is, do any of these only get covered by one of those 2? If they do, they're what we call essential primes because they're going to be in the answer no matter what. In this case, both of these are essential. Notice that this guy is the only guy that covers that term, so he has to be in the answer. This guy is covered by both of them. This guy covered only by the second guy. So we come back over and we can say y is equal to, well, what is this? A changes, B changes, only C hangs around. So y is equal to C, or y is equal to B. So this would be the answer to the problem. And we said that a while ago. If we put a circle here, that's B. A circle there, that's C. Y was equal to B or C. It doesn't matter which order you write them in. We'd probably write B or C. And we got from our truth table to an equation using the Quinn-McCluskey method. Let me back up a couple slides here. Let's review this to make sure that this still makes sense. In step 1, we go find all our minterms and sort them by the number of 1 bits. We then look at it and one in the next group. If they're different by 1 bit, which is the next step, we replace the bit with an X and put them into another column, which is when we do this, go back to step 2 again. We'll work on the next column. If we did a match, we check off the guy that was the source and the guy that was the destination. And if there's any duplicates, we cross them off. And we do this until we can't compare anymore. And what's left are our implicants. We put stars next to them in this picture. Any questions about this page? Now we build the prime implicant chart of the table of choice. We put the answers that we just got from step 1 as the rows of the columns, or rows of the chart. And across the columns, we put any implicants, not including any don't cares. We try to figure out which ones are essential first by picking the guys in the row names that cover columns that are only covered by that one element. They have to stick around. And then with the remaining columns, we try to figure out the best way to get those covered. And just going through it quickly again, we take out and sort them by the number of 1 bits. This implicant has 1 turned on, 1 turned on, draw a line, 2 turned on, 2 turned on, 2 turned on, draw a line, 3 turned on. Do the comparison. Everyone here against everyone in the next group. We get some X's in them. Now we compare everything in the top group against everything in the second group. Going to yield something with double X's in them. Now, this line is not really supposed to be here because this could never compare against anything else because it's 2 against 2. So if we kept going, we would have to have generated from multiple groups as opposed to just 2 groups the results. But we'll forgive him that. We did have some duplicates. We have to scratch the duplicates, leaving us with only those 2 as our prime implicants. Taking these as the table of choice rows, these as the columns, we build the table of choice. We come along, I can't write on this, but anything ending in a 1 is covered by this guy. And not necessarily by this guy. This guy could have covered him because there could have been a 1 here. But there could be some with a 0 in the middle and no 1 at the end, and then this guy couldn't cover him. So when we're done, we see that this guy has unique coverage. This guy has unique coverage. He has unique, meaning both terms are necessary in the end. Then we can simply write these out as our answer, and we're done. And then we double checked ourselves with the Karnow map. Here's another one. Why don't you see if you could group these into the minterm table? Group them by 0, 1, 2, 3, number of bits, and let's see how you're doing. Don't miss out on the fact that this does have X's in it. All the places there's X's here are don't care. They are considered minterms, but will not be considered in the table of choice. So just simply put this into the groups, and if you get done with that really quickly, you can start trying to see if you can make them compare. So take a couple minutes and get that done. I'm going to turn my microphone off for a second so I can give the cat some treats. She makes big meowing noises. That was easy. Okay, see if your grouping looks like that. Give me a green circle once you verified that that's the way you would pull those out of there. Okay, so everybody looks like they're doing okay. So let's think about it, and you can start trying to do everything in the one group gets compared against everything in the two group. Let me pull a piece of paper over there. I forgot one somewhere laying around here. So I'm taking 0, 0, 1, 0 and comparing it against 0, 0, 1, 1. So that's going to give me 0, 0, 1, x. Now I'm going to take 0, 0, 1, 0 and compare it against 0, 1, 1, 0. It's going to give me 0, x, 1, 0. You guys check me out here as I'm going along here. Same one against the third one. In this case, there's too many different. We can't do anything with him. So the 1, 0, 0, 1 will not get checked off because of that comparison. And the last one is 1, 1, 0, 0. And again, there's too many things changed between those two. So my second column now contains this guy and that guy. He has a check next to him, and the first two have a check next to him. So now I go to the next guy. Compare him against the first guy. Too many change. Compare him against that. Too many change. Compare him against this. And that's good, 1, 0, 0, x. So now this guy has a check, and he has a check. One more to go. This guy here. Will give us a 1x, 0, 0. So now in the next column, we have those two x's up here and the two down here. And everything in this set has a check next to it. And everything down here has picked up a check mark, meaning they're not going to be ultimately used for something, but we can't toss them out until we've compared everyone against everyone down here. So every 2 has to be compared against every 3. And then every 3 has to be compared against every 4. So if one of these had not had a check mark from the top box, it might pick one up when it's compared against the 3 box. And we'll get this. Ultimately, everybody does get checked off. We've got these guys, and these guys. These guys were yielded from having 1, 1. They were compared against something that had 2 1s, so we know the other one could be a 0 or a 1 in those two groups, which is where the X's are. So the difference between this group and this group are the fact that now this is going to have 1 1, this will have 2 1s, this will still have 3 1s. But the fourth one got taken away because the 3 covered him and he didn't have anybody to compare against. So now again, we're going to compare every item in this against every item in this, then every item in this against every item in this. But the shortcut is we only have to compare where the X's line up. So the first guy only has to be compared against this guy and that guy. The second guy can only be compared against things that have an X in the second position. That would be this one and that one. Again, only against the fourth position, which is here and here. And this guy only against the second position, which is here and here. Notice none of these have an X in the first position. So this guy will not get checked off as a result of these. But notice when he gets compared against the next group, there is an X in the first position, and X11X will cause both of them to be compared. So once we've done that column, we're going to wind up with something that looks like this. Everything will have 2 X's, but we still have 2 groups. These are the ones with 1 1. These are the ones with 2 1s. Notice also in here, there's a bunch of duplicates. Now, when we compare, this guy has to be compared against somebody that has something in the second and the fourth place. None of these do. So he can't be compared against anybody. This is the other guy. He's also second and fourth. Can't be compared against any of these. So once we get rid of the duplicates, we have our prime implicates. Time to build the table of choice. These are the labels of the rows. These are the labels where these guys are the labels of the columns, but it's better to look in the truth table because we're not going to include any that have X's. Notice also here that we could have had some things left over in this row that never got checked. In this case, we got rid of the duplicates and they became, but let's say one got kept because it wasn't checked. We could have a star over here that would have more terms. We'll put the least term ones first, the greater term ones in our table of choice. We don't have an example of that in here. So let's build the table of choice. Have you got yours built yet? I'll give you 30 seconds to get it sketched out. Okay, table of choice looks like that. We have 1, 2, 3, 4, 5. So there's only 5 columns because that's the only place where there's a true. The don't cares we don't use. Remember, the algorithm takes care of picking zeros and ones correctly to minimize things for us. So now we have to look. This guy is going to cover anybody that starts with 2 1s. What's this last guy? This guy's going to cover anybody that has the center 2 turned on. That's any of the last 3. He's going to have the first one on and the third one a 0. Do we see one of those anywhere? Any idea why we don't see any? What, Robert?
Because all of those answers had X's, not ones.
Right. Those were, and this is an example of it getting rid of something for us. We didn't accidentally have to create that extra box because it's not going to cover anything. Here's another one, starts with a 0, third one's a 1. There's this guy, this guy, this guy, this guy. Okay. Why don't you take a shot at putting in your coverage markings and then see if there's any essential primes. Are there any of these terms that are the only one that cover one of these? If so, it's necessary in the final answer. And then once you've done that, see if you can figure out what the best other coverage is in order to solve the problem. There may be multiple answers to this. So give it a shot. Think about it a second. Is that the coverage you got? Well, the first two can only be covered with the last guy. So the last guy is an essential prime. Now, we can pick him, plus we can pick this guy, because it would be a box that added some new material, and everybody is covered, meaning we would not need that guy. Or we can pick him, not pick him, and pick him, in which case everybody is covered. Either of those answers is correct. This guy is essential, though. He will appear in either answer. So our answers are either y is equal to not AC or AB, or y is equal to not AC or BC. So let's look at that down here in the truth table. Not AC is this guy down here. Where does he live in the table? Not A, C. So it's these four right here. The only way to cover those four are to draw a circle around them. Now, this one that's left over could be covered by making those four be picked, or in which case, what's that little box called? That little box is called BC, second answer. Or it could be use this box right here across the screen. Both of them have four elements, so both are just as good. If this guy were picked, it would be AB. So both of these are correct. These are minimum subproducts. Everybody see how we could check that with this and how it took care of getting rid of the ones we didn't need for us? Pretty cool, huh? There could be an art here also of picking these when they become large, but that's a skill I think all of you basically have. How about this guy here? Lordy, how many inputs does this one have? A, B, C, D, and E. So that sounds like 5 inputs. We can group them. We can do the matching. We can check them all off, but we would find these 3 did not combine with those. So they're going to remain around even though they have 4 terms in them. This guy is actually going to compare and go from his terms by getting rid of duplicates down to this. They're all going to compare, leaving us only with this one guy here where the duplicates can get rid of it. So we have a single guy of 2 terms, and we have 3 guys of 4 terms. Table of choice says they're going to look like this. Notice we put the best one at the top. We pull the ones out of the other table, and we get this. Now, which of these are essential primes and which ones do we not necessarily need? What what is the top guy cover anything as an essential prime?
Yeah, the first, second, and last one are essential, I think.
Okay, this guy's essential because he covers he's the only check mark in that column. Only check mark in those columns. So he has to be there or else those 8 would not be covered. This guy is only covered by the second guy. This guy is only covered by the last guy. So the real question becomes, do we need the third guy at all? Or is he already covered by other people? Give me a green circle if you think we need him. Yeah, red circle if we know it. Yeah, this guy is automatically covered because he's essential and already, because he's covering him and him, this guy doesn't buy us anything to cover him. Same thing over here. Now notice in the equations that we kept, he has 2 terms. He has not B and not D. These guys, this is A, B, D, E. He has 4 terms. He would have had 4, but we don't need him. He has 4 terms, not A, B, C, D. So when we write out our equation, you see we can keep 3 terms, although they're different lengths. This is the best guy right here. He's the shortest, and he bought us the most, even though these are pretty good because we still, remember this is a 5 input problem. We got it down to 4, and anytime you can get rid of any terms, it's going to be easier to build. Of course, this could be checked in the Karnow map. We would need to have the 2-level Karnow map to check it, and I leave that as an exercise for you to do. This is a homework problem. Basically, use Quinn McCluskey to come up with your answer. Double check. It only has 4 inputs. So double check it with Karnow. When you're done, notice it does have at least 1 don't care. I think that may be unique. And it's the last page of these slides. Okay. So real quick, I might lose you while I'm doing this, but let me go turn that on and see if I can get you to get it. Okay, I might lose you. If I do, I will come back. Is everybody still there? Give me a green circle if you are. Yeah, okay. If you go look under assignments, that slideshow should be there. And let me know if you give me a smiley face if you get it. Newmar, did you get it? Okay. And yeah, when you haven't gotten it?
Your screen is dark here.
Okay, well, you have to work out getting that and make sure you have a copy of it because your homework's the last couple pages of it. And you'll have to, if you don't have PowerPoint on your machine, you can get the PowerPoint by going to Outlook. And the way Mercer has it set up, when you get there, there should be a way to pick all of the Word programs, even if they run online, and be good enough to get it so you can copy it or print it or whatever you need to do. Okay, let us move ahead. Okay, what I want to do is I want to re-look at one of our transistor problems. You see, where do I have something I can write on? Here we go. And I want to look at the one we did. I just kind of put up there as, let's see who asked me questions about this one. We're going to have a transistor. And we'll ground the emitter. We'll come over here and we'll have a battery. Come up here and put a resistor. Go through a diode or LED. Put a little arrow on that. Through a resistor. And back to here. I believe this was plus 10 volts. And I probably didn't give you much else about the problem. And as we just call this LED 1. We'll call this RC. Call this RB. This is Q1. And this is VCC and VBB. We'll just call it V1 for now. Okay, give me a green light if you think the LED comes on when we hook this up. And yes, it's dependent on the values of the resistors. Our goal in lighting up the LED would be to put the transistor in what state? Yeah, I know, Nevada. Now, what state would we want to have the transistor in? Somebody pop your hand up. Scott, what state would we like?
We want it to be saturated.
Okay, so we want to have it saturated because if it's active, every little variation in the base current will cause the light's brightness to change. At saturation, we're going to use RC to set a fixed value for the current that's going to pass through the LED, meaning that the brightness of the LED is not going to change. How do we know if we were just measuring, poking around here with a set of meters and things, how would we know that the transistor is in saturation? What would be our tip-off? Two things we have to see. Raise your hand if you know. And Scott, you can still participate. Samir, what are the two things we need to know?
You need the VBE to equal 0.7 volts.
Okay, so we need this measurement right here, which is VBE, to be equal to nearby 0.7 volts. We've used that as a fixed number. It'll be variant of that a little bit, not much, in the ballpark. What's the other thing we would need, Stephen?
The VCE would have to be less than 7 volts.
7 volts?
Or sorry, 0.7.
Okay. So less than 0.7 volts. That's VCE. Now, kind of rule of thumb, if VCE, if this were 0.7 and this were greater, how would we be operating the transistor? In which region? Scott?
Active mode.
Yeah. So active region, which is amplification basically, says we're going to have 0.7 volts here, but the value of VCE is going to be greater than 0.7 volts. Basically, the diode that's on top will not be reversed, or will be reverse biased, not forward biased. Now, the other thing that we need to know about active is when we're in the active region, base current, so I sub B, times beta is going to equal IC. So this gets magnified by that value, which we estimate for our transistor to be 100 if you don't know otherwise. And if we're not computing beta, we'll use 100. So in this case here, if we had, a milliamp put in and we saw 100 milliamps coming out and we knew the beta was 100, we also would expect to find this value being greater than 0.7 volts because we'd be basically amplifying times beta. Now, if we're in the saturated region, then the current itself is not affected by beta directly. Instead, it's limited by the collector resistor's value. So Ohm's law says that I can only push as much current through here as the voltage divided by the resistance will allow. Meaning that if I'm limiting it with this resistor, I'm in saturation, and we'd expect to find a value less than 0.7 volts here because I can't multiply the base current times the beta and get a value that'll be able to be put here because the resistor itself limits it. That's what saturation is. So we know that if we are in saturation, basically measuring a voltage less than 0.7 volts here, what we know is that if we took the base current and multiplied it times beta, we would get a current that's bigger than the allowed collector current that we do have. If, however, we're operating where we can take beta and multiply it times the base current, and we get a value over here that's smaller than this would clamp it at, then we're going to be amplifying things. So this circuit, we could analyze it either way without knowing the resistor values. We can't determine whether we're saturated or we're active. But for a design purposes here, let's design it so that it is saturated. Our rule of thumb for doing that was let's take the desirable current that's going to go through the collector. Let's divide it by beta to get the current that we could put through the base. But since it's times beta, that would put us still in the amplifying region. And let's make it be too big, the current here, because if we make it too big, then it definitely times beta will have to be clamped by the resistance of the collector. Now, how big do we make it? How much bigger than 100? Well, that's kind of the art part. That is not necessarily going to be something that I can give you an exact formula for because there's a bit of art here. What the art says is, I don't really know what beta is. I'm guessing that it's 100 because that's what the teacher said it could be. But what would happen if it were smaller? What would happen if beta was actually 50? Well, if it was actually 50 and I had only divided this current by 100, then when I multiply it back, I won't be in saturation, I'll be in the active region. But what if it never got down to 50? What if it was only 75? Well, the values between 50 and 75 would cause me to have to pass more current through the base than's necessary. So making the base current arbitrarily big causes me to use more power and to heat up the circuit more. So what I need to know is I need to know a reasonable estimate for beta. So when I do that calculation, I'm doing something reasonable. Well, what we're doing is reasonable, not knowing, which is divide it by the beta and double it. Gives me a value here, which even if this dropped to 50, will still work. And if this rose to 200, would only be better. Yeah, it'd be a little warmer and things, but it's not ridiculous. It's not like saying, well, I'll just put a 10 ohm resistor here because I'm guaranteed to have enough current to force this in. Yes, you would, but everything would get really hot and we'd waste a lot of power. So what we need to do for a second is let's go take a look at the data sheet for a transistor. I think I have one here. Let me see. If not, I can open the page with one on it. I'm trying to avoid here knocking out URLs. Circuit, do I have one open already? I actually do. Okay, here's the data sheet for a 2N3904 typical small signal NPN transistor. It's one of the two major transistors of the NPN type bipolar family that you would have bought from Radio Shack when Radio Shack was in its heyday. That and something called the 2N2222A actually on the end of it. What we want to do is look at some of the data sheet for this so we can determine if we can figure out how to get this thing into saturation properly. Let me get you back where I can see your page. I think it's that one. Okay. So the chip itself has pins 1, 2, and 3. And it tells me that pin 1 is the emitter, pin 2 is the base, pin 3 is the collector. So I'd know how to plug one in order to use it. There's two different form factors. One is bulk, where they are not really hooked for automatic packaging. The other is in what's called an ammo pack. They look like bullets on a belt, and they basically are able to be ripped off and soldered by a machine directly onto a circuit board. And you can buy them. They're usually cheaper in an ammo pack than they are in bulk when you buy them in bulk. Okay, so here's the maximum rating. We, on this particular chip, don't want to ever pass more than 200 milliamps through the collector. Okay, we won't. These are some voltages. If you didn't hook up the third one and you just hooked up two of them, what would be some maximum value? All those are pretty big except for the emitter base, which doesn't want to have greater than 6 volts over it. But we'll always put a resistor there, so it won't matter. Now, data that's going to be important to us would be in this second chart here. In particular, when the collector emitter are saturated, basically the highest the value will be is 0.2 volts, 200 millivolts. We've always just said, well, it's going to be less than 0.7. Well, yeah, it's also going to be bigger than 0, but it's only going to be at most 0.2 volts. So it's so small, we don't have to work with it. We can still use a 0 there or even 0.7 and it'll work reasonably. We have two values because they do it for two operating points, but they're the same value, so we don't care. When we're in saturation, the base emitter needs to have a value, low value of 0.65, highest value over here is 0.95. So it's going to be near 0.7 volts, which is what we wanted it to be. Our usage is nearer to the 10 milliamps than the 50 milliamps, so we probably won't see something higher than 0.8 volts. Probably because that's a maximum. If you look at the top of the columns, typical is left just floating somewhere between. Now, the next one's quite interesting because this is HFE. HFE is the same as beta. It's just a different name for it. It says when you're operating at this particular collector current and you're operating as an amplifier, because that's the only time it matters. This is the low end of being an amplifier. Kind of best practice design would make that as low as you possibly can so you don't waste anything on amplifying. You're going to get these values of beta. We're operating closest to our collector of being 10 milliamps. We really want 20. We also don't want to be saturated, but it'd be a good idea to know what beta could be. Beta could be as low as 100. It could be as high as 300. Remember, we said bigger is much, much better for us. But we also designed it so if it got as low as 50, it would still work. So assuming we were driving our LED at higher or lower currents, the lowest it ever gets is 30 when we're passing a lot of current through the collector, in which case our divide by 2 won't work. We probably have to divide by 4 or divide by, well, 3 would be pushing it, so divide by 4. However, for the rest of these, if we manage to get our betas down that low, we still already kept ourselves into the saturated region and certainly have for the region we've said we want to operate in. Typically, I've seen these operating about 200, which they don't write the number down, but you can extrapolate it somewhere between here. And if we were to run this in an emulator, we'd see that would be one of the reasonable values that we would get. And then it has other values like how fast can you make changes and all those sorts of things. The other thing is typically when we're operating an LED, let's say we turned on the LED and it was too bright. We do not dim the LED by reducing the current. Instead, what we do is we turn the LED on and off so fast a person can't see it, but the amount of time that it's on is going to be averaged out by our eye, just like frames in a movie. And we might have a 50% duty cycle, for example, meaning it's on for 50% of the time and off for 50%. But if we flash it at more than 30 times a second, it will appear to be on all of the time to us, but it will appear dimmer. By doing that, we also don't have to worry about accidentally dropping into the active region. We're going to continue operating saturated, but we're going to be using a modulation form called PWM, pulse width modulation. Pulse, P-U-L-S-E, width, W-I-D-T-H, modulation spelled just like modulation. And we'll keep that in mind because later on we will, in some of our real, when we use our Arduinos later, probably actually do some pulse width modulation. So just be aware that this is where we would come to find that. Now I mentioned emulation, and it's really easy to find emulators online that can emulate transistors, and I know a couple of you have. I have one here we're going to run a little test with. It's called 5-Spice. And over on the left there, or in the center of your screen, I built the circuit we have on our thing. Here's a 10-volt battery. It's grounded. Here's a transistor. I'm using a 2N2222 because I simply didn't have an emulation model for the other one, but they're virtually the same. This is a little faster. Doing some calculations, one of you did. Who was it? Was it Scott that did some calculations for me? Remind me.
Yeah.
Yeah. He told me that we needed this to be a 22K ohm resistor and we needed this to be a 390 ohm resistor in order for this to be properly saturated and for these to be in the reasonable range that we've talked about. I also threw on here a measurement of the current for the base, a measurement for the collector current, which is what the LED is going to see, a measurement across VCE, and a measurement across VBE. So we can look at those. And it looks like I also measured across the LED to see what it was going to drop. So what I can do is I can run this emulator. Now, in this class, when we do this, some semesters we don't actually use the graphic emulator. We actually use the code that's being written behind the scenes. So when I run this, and it gives me an answer. Normally, we would be using this as our thing, and I didn't have any notes here, but we'd be able to see the actual program that we just ran, and we'll find that in here, because we're using a user interface, and if you're using LT Spice or one of the other emulators yourself just for fun, there's going to be an answer page where it tells us what happened. So I know you probably can't read all the numbers, but I'll tell you the important ones. VCE for our transistor came up as 0.11. So is that's less than 0.7. So, and it's close to the 0.2 we were expecting. So that means VCE is indicating to us we're in saturation. VBE is 0.71, which is great. That means the transistor's base emitter is being held right at, the correct spot. The LED I have is only 1.9, but if you go to 2 significant digits, that's 2.0, which is still awfully close to our 2.1. So we're getting a correct voltage across the LED, which also, though, could explain some of the differences in the other two numbers. Although my guess is the fact I'm using a 2222 is going, because the beta I would use there would be 200, not 100. However, in this circuit, I probably would have used 100 because, yeah, I probably would have. So we'll get similar results. So the base current we have is 420 microamps. The collector current is 20 milliamps. So if I grab a calculator, I think I have one open, and I take the collector, which is 0.02, and I divide that by 0.00042, I'll see that my beta would have been only 48. Well, we know this guy doesn't have a beta that low. We've also have really good evidence that it's saturated. So because of that, we can be pretty sure we're operating everything correctly. If I go back here and I change this value so we're not getting as much current to the base, I'm going to change it from 22K up to 170K. And I rerun the analysis, and I go back here and I look, I'm going to see that VCE right now is 4 volts. VBE is 0.69, which means it is close to 0.7, meaning we're in the active region. VLED has the same amount dropping across it, of course. The base now is only putting, I'm sorry, I'm reading the battery voltage. The base current is very small right now. It's like 0.05. And the collector current is only down at 10 milliamps. So if I take 10 milliamps, and I divide it by 0.00054, I think is the number. Notice I'm operating at a beta of near 185, which is probably right. That's the active region. And so the beta at this point is about, it's less than 200, but remember we said the beta is going to be somewhere between 100 and 200 when we're in the active region. And it's legitimately getting that because we have a voltage of 4 volts across VCE, which means it's not, we don't have the reversed BC junction, and we're definitely operating like an amplifier. So if I were operating at this, I don't think I have an easy way to grab those two numbers and do the literal division so we could see what this really is. This is not really going to be 185. It's going to be somewhere in that ballpark. But I would be able to do that. Now, the other thing that is possible to do here, and I mentioned just to kind of as a caution to you, we had 22K here as or 170K as my value for the saturation, or for the active region. Remember, we had 22K. What if we change this so that it was only 1K? And we ran it. Well, we'd see VCA is down at 0.03. It's very low, which we'd expect. VBE is a 0.7. LED is at 2 volts, which we expected. But notice that we're still getting 20 milliamps for the collector because we're running in saturation. That won't change. But notice now, instead of 400 microamps, we're pushing 9 milliamps through the base, meaning our power on the base has gone up significantly. The wattage we're using to get exactly the same result on the LED is a lot more. So that's why we don't just pick an arbitrarily low number. Algorithmically, we're going to divide beta by 2. We're going to divide the collector current by 2 and then double that value so that we get a reasonable number that'll handle pretty big excursions of beta without excessive power use. Now, if you recall, in the other circuit we have, which looks like this, one of the things we said we could do is we could replace this with the output of an integrated circuit chip, and we could either turn it on or off, and it in turn would then turn the LED on. And then we said over here, if we put the chip here, the same thing would happen. The LED would come on. Now, question for you here. Why would this be a dumb way of doing that compared to this? Anybody have any good answer to that? Why would this not be a good way to do what I just said? I'm going to replace the battery with a chip's output, which is either ground or 10 volts in this case. Or in this case, I'm going to replace it with ground or whatever I put here, 3 volts. Why would this be a better circuit than that? They seem to accomplish the same goal. Of course, so did the battery. Remember when we had a battery, 1 resistor and an LED? That also just turned on the LED, and we could have replaced the battery. Why didn't we do that? Why is this the preferred circuit of the 3? Scott, what do you think?
There's definitely something better about having a separate voltage source for the LED apart from the switching.
Absolutely, you're right, spot on. If I put the pin here, I not only have to provide the base current, I have to provide the LED current. Well, the reason we came to a transistor circuit in the first place was because when we had a circuit that looked like this, and I said, we'll replace this. The reason is because this had to supply 20 milliamps. Now in this circuit, we not only have to supply the 20 milliamps, we also have to supply the 400 microamps. So this is worse than this. However, this guy says if I make this my pin, I only have to supply the base current, 400 microamps. This battery or power over here will supply the 20 milliamps I need to drive the LED. So that's why we picked this circuit for a saturation type of situation where this ultimately is going to change to being the output of an integrated circuit, something that has very limited output. It probably would burn it up over here, just like it would have over here if we just put the circuit in here. Neither of these are good. And this one, although fancy and demonstrates everything we'd love to know about, is not a good way to make the LED come on. And if we replace the LED with a motor, this guy definitely wins because he has his own separate power supply, which can be a different voltage from this and definitely produces different current than the controlling current. Any questions about that or that last little discussion? I know that's fairly advanced, but we need to know it. You guys have fun tonight? Give me a green light if you had fun. Nobody gave me a green light. Oh, I'm so sad. Well, we did a lot. You have a homework assignment besides just reviewing your notes. And the homework assignment is to do that last Quinn-McCluskey problem and be prepared to turn it in, but I may or may not collect it on Wednesday. And on what are we doing on Wednesday? Let's look at the syllabus here. We're going to start applying some of the things we know to arithmetic and to what we call digital components, which are functional units, like arithmetic is actually a digital component. And we're going to talk about one of the types of integrated circuit chips where I'll actually show you what's inside one and you can analyze the circuitry of transistor logic, or TTL. It's an older, outdated, not outdated in the sense it's not used, but some of the families have been retired. But it gives us a good example to look at. Because later on, we get down here where we're actually working with hardware, knowing about the hardware and how it integrates with what we've been talking about, instead of being so kind of ethereal, it'll actually be something that we can sink our teeth into. So be prepared to talk about digital components and implementing arithmetic. Make sure you've done your homework and, review any of this, because it's not going to be that long until you have to do some Unicode problems again, or you're going to have to do some 2's complement or whatever's in this list. It's all fair game on this first exam down here. We got a lot more to cover, a lot more technical stuff. Any last comments? Okay, then I'll tell you good night if you'll